Hello.
Hello.
Yeah. Okay, so we'll continue with gravitation and electrostatics. So the first thing that we'll discuss is basically the definition of gravitational potential energy.
It's maximum 100.
What? Can everyone hear me?
Sir, your voice is a bit low.
So I can hear you. Like it's fine for me.
Hello? Can you hear me now? Arjun, you have to say something.
Sir, I think it's a bit better now.
Okay, so gravitational potential energy. One second, just hold on. I have a call. I'll just get back in 1 second. Hello. Can you hear me?
Yes, sir.
So we'll start off with gravitational potential energy. So because the reason is that once we understand potential energy, we can define gravitational potential. And once we know how to calculate potential, that will give us a way to calculate field easily. So there is a connection between all of these things. Potential and field, there's a major connection. And the reason we are taking this approach is that if we saw in the last class, if there are multiple particles and there is some point here, and if we want to calculate field at this point, gravitational field, then obviously each mass here will create its own field, right?
Yes, sir.
Yes, sir.
Each mass will create its own field. And then for field at this point, E resultant, you will have to take the addition of E1, E2, and E3 vectors, right? So
Yes.
the problem is that ultimately, like, you'll have to do vector addition of all of the fields, and vector addition is more complicated because you have to take care of directions and stuff. So if there are many particles in a body, then calculation of field is a little difficult because all the time you have to worry about the vector direction of each field. So that is slightly harder. On the other hand, when we define potential, potential is a scalar quantity. Potential is a scalar quantity. So when you have some particles like this, and if you want to find out potential at this point, that will be much easier because it will just come out to be some number. Potential due to this will be some number V1, then V2, V3, and you can just simply add them, right?
Yes.
That time, if it is a scalar quantity, your addition becomes very easy. So calculations of potential are generally much easier if you have a system of particles than calculation of gravitational field. And because there is a connection between field and potential, once you know the potential, you can find the field easily compared to directly trying to find the field. So that is what we'll try to do. We can do direct field calculations also first, but we'll start off with potential because it's easier to do integrations when it is scalar quantity. Is everyone understanding what I'm saying?
Yes, sir.
Okay, so the first thing that he is talking about is gravitational potential energy. So we know that gravity is a conservative force, is conservative. What is the conservative force meaning? What is the meaning of conservative force? Nobody knows conservative force.
Sir, initial and final force will be the same.
That statement doesn't make any sense.
So the work done doesn't depend on the path taken.
Initial and final force, what is that? Work done doesn't depend on the path taken, or work done only depends on initial position and final position, not on how you went there. That is the definition of conservative force. Gravity is a conservative force means that if I take a body from this height to this height, work done by gravity does not depend on how it went there. It only depends on the difference between the heights. Right?
Yes, sir.
For conservative forces, it was discussed in chapter 8 or work by energy chapter that you can define a quantity called potential energy, and you can say that work done by a conservative force is equal to negative of delta U for that force, potential energy due to that force, right?
Yes, sir.
So work done by gravity will be negative of delta U due to gravity. So that means U initial gravity minus U final due to gravity. So the way potential energy due to gravity is defined as U initial minus U final is equal to work done by gravity, right?
Yes, sir.
So in general now, what we will see is a case where say some mass is here, capital M, and some mass is here. Let's say the initial distance between them, this is the initial position, is Ri, and the final position is here, and this is Rf. This distance is Rf, and this distance is Ri. Now, gravity was acting on the mass in this direction, force of gravity. So work done by gravity in going from mass m going from here to here would be, work done would be integral of initial to final F dot dr, right?
Yes, sir.
F dot dr. This work done would be positive because gravity is pulling it this side and it is coming this side, right?
Yes, sir.
The final answer should be positive. So you will get G m1 m2 by r square dr and integrate it, and from Ri to Rf. Obviously here you have to be a little careful, but if you know that the final answer is positive, then you don't have to worry too much, because technically you will write force as minus G m1 m2 by r square, and then dr generally will be this direction, right?
Yes, sir.
dr is generally this direction, force is this direction, so it becomes minus minus dr and it becomes plus, right?
Yes, sir.
Finally, you'll get after integration minus g m1 m2 by r, and you'll put ri rf, and when you put this, you will get, you should not put a minus sign because final answer has to be positive. So you can just say g m1 m2 1 by, which direction makes it positive? 1 by rf, 1 by ri minus 1 by rf, right? That will make it, no, that will make it negative. So it will be 1 by rf minus 1 by ri. This will be the work done, right?
Yes, sir.
Yes, sir.
Like the reason it is a little confusing is because force direction you have to take in this way, dr is this way. You have to keep track of directions, but keep in mind, like whatever comes expression, the magnitude has to be positive because work done you can clearly see is a positive work here, right? So therefore 1 by rf must be in the denominator first, because then that makes this quantity bigger than this quantity because ri is greater than rf, right?
Yes, sir.
Is everyone understanding what I'm saying?
Yes, sir.
So if work done by gravity is this amount, then that is equal to minus del u of gravity. So that is g m1 m2 1 by rf minus 1 by ri, and that makes ui minus uf is equal to g m1 m2 1 by rf minus 1 by ri. And that just suggests that, okay, can I split this expression into two parts and call one of them ui, one of them uf? Yes, you can if you define u as minus g m1 m2 by r. Because then when you put ui, you say ri, and when you put uf, you say rf. And then that will be the difference. Ui minus uf will become this, right?
Yes, sir.
Correct. So this is the definition of your potential energy between two point masses which are separated by a distance r. There is a minus sign here, which suggests another thing. U is coming out to be this minus g m1 m2 by r. This means 2 point masses m1 m2 separated by a distance r, which suggests one more thing, which is that anytime point masses are separated by a finite distance, are separated by a finite distance, its potential energy will always be negative. right?
Yes.
Yes, sir.
For any distance between point masses, everything inside here is positive. So this whole potential has to be negative. And if R tends to infinity, potential energy tends to zero, right?
Yes, sir.
So the reason this is important is because later you will see cases like bodies escaping from the earth and things like that. Like what is the escape velocity and how much energy needs to be supplied to a body so that it can escape the gravitational influence of another body and all. So in all those contexts, you have to keep in mind that truly escaping the gravitation of a body will happen only when you are making the separation between yourself and the other body to be infinity. Because at infinity separation only you can say that force due to that body is zero, right?
Yes, sir.
So basically you are saying that if you have to escape the gravitational field of a body, you have to go to infinite separation from that body. So your final potential energy should become zero. So many times such questions are solved by doing this. You'll say that, okay, there is a satellite revolving around the earth and all. And what energy has to be supplied to this satellite so that it can escape the gravitational field of the earth? So one easy way to do that is to say that, okay, right now my initial potential energy of the system is something, right?
Yes, sir.
I want to and total energy of the system is also something because this has some kinetic energy also. So you will say total energy is K plus U, right?
Yes, sir.
If this body has to escape, you want to give it enough energy so that it is just somehow managing to reach infinite separation. And if it reaches infinite separation, you can say that maybe kinetic energy becomes zero at infinite separation. Because that means that you have just barely managed to reach that point, right?
Yes.
Yes, sir.
Because if you think about it, if you give it, if it tries to escape, as you go farther, your kinetic energy becomes lesser, right? Because
Yes, sir.
gravity is doing negative work on you. It is pulling you back, but you are somehow trying to go away. So your kinetic energy will keep decreasing as you move farther and farther, right?
Yes, sir.
So you want to give it enough of a kick here or enough kinetic energy here extra so that it reaches infinite separation with k is equal to zero at infinity, right? So you can say total energy final should be k final plus u final. And in order to reach infinite separation, kinetic energy final, let's say, is zero, and potential energy final is also zero. So if you realize that, then you will say that, okay, all I need to do is to provide it enough extra energy so that its total energy can become zero. Right now, total energy will always be negative. Total energy being negative means it is in a bound situation. It is revolving around the planet or something like that it is doing, right?
Yes, sir.
Yes, sir.
So when you calculate k plus u, it will come out to be some negative quantity. You want to give it extra that much quantity to make its total energy zero. That means it has the potential now to escape till here, right?
Yes, sir.
So this thing is important to realize because that will help you solve like questions like these, like how much energy does a rocket need to be able to escape the Earth's gravity and stuff. You need enough energy so that its total energy of the rocket becomes zero. When the rocket is on the ground, if it has some velocity, it is still in the situation where it is in the Earth's gravity field and its total energy will still be negative. You want to give it enough velocity so that it can overcome the total energy is equal to zero barrier, right?
Yes, sir.
Anyway, now coming back to the potential part, once we have defined potential energy, change in potential energy becomes simply U final minus U initial. So you can just say G M1 M2 by R final minus G M1 M2 by R initial. That is your expression for change in potential energy. And now we define a new quantity called gravitational potential. Gravitational potential, which is defined as change in potential is equal to change in potential energy by mass. Basically, it is whatever mass is moving. Suppose you have a big body here, capital M, and a small body here. And the small body moves from this position to this position, right? So obviously, it has some UI here and it has some UF here, right?
Yes, sir.
And this is your Ri and this is your Rf. So the way potential, change in potential is defined is what is the change in potential energy divided by the mass that was moving. So here you will have V final minus V initial will be U final minus U initial by small m. The small m was the mass that was moving. So this comes out very simply. It becomes U final minus U initial is minus G m small m by Rf minus minus, so plus G m small m by Ri divided by small m. So that becomes Vf minus Vi, and small m will get cancelled throughout, and you will say Vf minus Vi will become minus G capital M by Rf plus G capital M by Ri. So you can define potential V as minus G capital M by R. And if you put Vf and Rf and Vi and Ri, you will get the required relation, right?
Yes.
So basically, potential is defined in terms of the source mass. Like this source mass is creating a potential at this point, and it is minus G capital M by R. And this source mass will create a different potential at this point because the small r is different, right? If you multiply that potential by the mass small m, which is moving, you will get the potential energy of the system. Is everyone understanding what I'm saying?
Yes, sir.
Yes, sir.
So in the V expression, always it is due to the mass that creates the potential at some place, not the small mass that is moving around and all. If you write potential energy, that has both of them because energy is due to the system. Potential is due to whatever created that potential, right?
Yes, sir.
And you need to know that this relation, like there is no other meaning to this V term other than this definition. Like you don't have to think of it as something new or anything. It is just potential energy per unit mass. So change in potential energy per unit mass is the change in potential. And in general, what matters in these situations is not the exact value of the potential. What matters is the change most of the time. Because you could have chosen a different setting where basically it's like saying the sea level doesn't matter. What matters is when you measure the height of a building or something, you measure it with respect to a baseline, right?
Yes, sir.
So the baseline can be changed and the height values for everything in the world will be different. But that doesn't make a much of a difference because ultimately it's the difference in height that matters for work done and stuff like that.
Yes.
Right? So all of these cases are being discussed with the implicit understanding that u at infinity is 0. If u at infinity is 0, therefore you are saying ur is minus gm m by small r, right? If someone
Yes.
tomorrow changes the definition and says u at r is equal to 100 is 0, then all the other values of potential will also change corresponding to that. But ultimately it doesn't matter because delta u matters. In work done calculations, delta U matters. So individual values of potential don't matter so much. So similarly, because delta U is the crucial thing, delta V again is the crucial thing in calculations. Choice of origin is generally not super important, but our standard choice of origin is that U at infinity is 0. And from there, these formulas are coming. right?
Yes.
Okay. So potential due to a point mass at a distance r from the mass is this. And now if you look at section 11.5 in gravitation chapter, then he will start describing different situations. There are 4 or 5 derivations that are shown. So those derivations are very important. You need to know how to calculate potential in different settings. So we will look at B first. B derivation is due to a ring
So what's the page number again?
207. Potential due to a ring at a point on its axis. So this is the situation. The radius of the ring is A. The mass of the ring is m. This is a uniform ring of mass m. Uniform ring, mass m, radius a. You want to find out potential at a distance r on the axis of the ring. On the axis. So these are the derivations where you will be using integration. So the idea here is simple. We know potential due to a point mass is minus gm by r. This is due to point mass. But now it is no longer a point mass. It is a uniform body. So every point on the body, you will break the whole ring into small portions. So this is, let's say, some small portion. It has mass dm. And similarly, there will be any other portions on this whole ring. Now, due to each of these dm's, there will be some potential here, right?
Yes, sir.
That potential dv would be minus g dm by whatever is the distance between this dm and this p, right?
Yes, sir.
Now, if you think about it, it's like this. A ring is like this, a circle, and then on the center, there is the point here at a distance r, and the point dm was here. So this is a, this is r, so this is Pythagoras theorem. So this is root over a square plus r square, right?
Yes, sir.
This is root over a square plus r square here. And if you realize every point on the ring will make the same angle and it will be at the same distance, right? Because the point P is on the axis, that's why.
Yes,
Correct?
sir. Yes, sir.
So this dv is this. And the easy part here is that now dv is a scalar quantity because potential is a scalar, doesn't have any direction. Because it is a scalar, we don't have to worry about arrows and all. It's just a number value here, right?
Yes, sir.
If we were calculating field and all, then it would matter how, which is this direction and all. But it's not going to matter right now. It's just a quantity, it's a scalar quantity. So if you integrate dv over the whole body, you will get the potential due to the entire ring. So it will be integration of minus g dm by root over a square plus r square. And if you see carefully, both a and r are fixed here because neither the point is moving, circle radius is same, everything is fixed. The only thing that matters here is the dm. So these are constants, they come out. It is minus g by root over a square plus r square, and integration of dm will be total mass capital M, right?
Yes, sir.
So this gives you your potential due to a ring, and it comes out to be V is equal to minus G capital M by root over a square plus r square, where the point P was on the axis of the ring at a distance r, right?
Yes, sir.
That is simple enough. Then he looks at a slightly more complicated derivation. If you see C, now he's talking about a uniform thin spherical shell. So what is a spherical shell? It has no mass anywhere except on the surface of the sphere. And this is a spherical shell, and he has drawn a element like this. This is like a ring element. You have to imagine it as a ring covering both sides, right?
Yes, sir.
What he's going to do is the case of potential at a point P, which is on this center line through the center of the sphere. He will eventually do it in multiple cases, whether it is outside, inside, and stuff like that. But right now, we'll mark it as having a distance of r from the center of the sphere. So O is here, P is here. And this derivation is super important because again and again it will be used later. So look at it carefully now. The radius here is A.
Mhm.
So how do you define a spherical shell? You will say that, okay, if I change the angle slightly, I will get another point here, right? On the other edge. So what he's saying
Yes,
is
sir.
this angle is theta and this angle is theta plus d theta, right?
Yes, sir.
In between the two angles, you can mark out 2 points and then you will rotate it along the whole sphere to create this shell, right? Are you understanding what I'm saying? If you have a
Yes,
ball,
sir. Yes, sir.
like you make two radiuses which are very close to each other, having only d theta separation. And if you rotate any line like this, you will mark out two like this. Right? There will be a shell here.
Yes, sir.
So the thickness of this portion is a into d theta. D theta was the angle difference here,
Mm.
right?
Yes, sir.
And what is the radius of the shell? Radius of the shell will be this, right? So if this angle is theta, it will be a sine theta.
Yes, sir.
So this radius is a sine theta, a sine theta. And the thickness here is a d theta. So why are we doing all this? Because all the mass m is on the surface. So somehow you have to capture the whole surface of the sphere to be able to integrate it and all. So we have created a ring on the surface now, because just now in the previous derivation B, we know what the potential due to a ring is on the axis at a point P, right?
Yes, sir.
So this shell is like a ring now for us. What we first need is the mass of this ring, right?
Yes, sir.
So mass of the ring will depend on how much area is in the shell, because mass depends on surface area in this case, right? There is a surface area, surface mass density, which is m by 4 pi a square, right? The whole mass is on a sphere of size a, therefore area mass density would be this.
Yes, sir. Yes, sir.
So then to calculate dm, we need to multiply dm with basically the area of the shell with the density, mass density. So
Yes.
area of the shell is what we need now. To find area of the shell, you can think of it like, okay, if I have a circle, I have a perimeter here which depends on the radius of the circle, which is a sine theta, right?
Yes, sir.
And since I have a perimeter, if I multiply it with the thickness here, which is very small, it will become the area. Like the perimeter of this multiplied by the thickness will become the area, right? Perimeter of this circle is 2 pi a sine theta. That is like a length. And if you multiply it by the thickness, which is a d theta, it will become the area.
Yes, sir.
Yes.
Is everyone understanding what I'm saying?
Yes, sir.
You
Yes.
have a circle like this and another circle like this. What matters is the gap here. Like you can multiply perimeter and the gap. That will give the area. Right?
So, but the perimeter of the other circle, that will be bigger, right? It's not going to be the
That is
same
why
as.
you are taking it as a small angle, that you will consider it constant.
Okay, yes, sir. Yes, sir.
If you have to consider it different, then what is the point? Like then you can different.
Yes, sir. Yes, sir. Yes, sir.
The perimeter is this, the area is this dA. So dm will come out to be sigma, which is m by 4 pi a square multiplied by 2 pi a square sine theta d theta. This becomes m by 2 sine theta d theta. That is your dm. Once you have dm, we know your potential due to this dm on the axis. Potential due to this dm on the axis will be defined by dv is equal to minus d g dm by whatever is the distance of this point from this point, right?
Yes, sir.
That has been marked as z in the figure. This distance is marked as z. So we'll say g dm by z. So now this is the expression z. Now we'll find a relation between z and theta and all, because the dm has come as minus gm by 2 sine theta d theta by z. This is your dv. You need a relation between this sine theta d theta and z and all, then only you can integrate, right?
Yes, sir.
You will be varying your integral dv and you want to actually integrate over theta ideally, because say theta goes from 0 to pi. But we'll first have to find a relation between z and this. So for that, he is doing cosine rule in triangle OAP. If you see triangle OAP, this point is A, this point is P, and this angle is theta. Then if you write cosine rule, cos theta will be equal to cosine rule, everyone remembers, right?
Yes, sir.
Cos theta will be equal to a square plus r square minus z square, a square plus r square minus z square by 2ar. So you get 2ar cos theta is equal to a square plus r square minus z square. And if you differentiate this, you get this side you're differentiating with respect to theta. A and r are anyway fixed here. That is not changing. Only thing that is changing is theta and z, because if you change theta, z changes, right?
Yes, sir.
If you change theta, you get a different shell, which is at a different z. But a and r are always fixed. So if you differentiate here, you'll get minus 2ar sine theta d theta. And this side, this is 0. So you get minus 2z dz, right?
Yes, sir.
You get ar sine theta d theta, it is equal to z dz. And then you can say sine theta d theta by z, right? Sine theta d theta only, you can say z dz by ar. That is what he has written, right?
Yes, sir.
So sine theta d theta, if you replace here with z dz by ar, you'll get minus gm by 2 z dz by z ar. Z cancels. You get minus gm by 2 ar dz. dv is equal to minus gm by 2 ar dz, right?
Yes, sir.
Once you get this, now it is about integrating with respect to z such that you can cover the whole shell. You have gotten due to one shell what it is. You want to ensure that you cover the whole sphere. So now there are multiple cases. So what he does is, case one is that the point P is outside the shell, or basically your r distance is greater than a, right?
Yes, sir.
If r distance is greater than a, what will happen? So you will say case one, r is greater than a, then integral dv will be integral of minus gm by 2ar dz. these parts are constant. So all you have to think about is what is the limiting values of dz as you bring the shell here, smallest shell, and here shell, right? These are the two extreme cases. So those two extreme cases, what are the values of the z, right?
Hmm.
So here the z would be, if it is a tiny circle here, the z would simply be r minus a, right? Because r is this much
Hmm.
and a is this much,
Okay. Yes, sir. Yes, sir.
right?
Yes, sir.
Yes, sir.
And if there is a small shell here at the other end, the distance here, z would be r plus a. Right?
Yes, sir. Yes, sir.
Because r is from center to here and much is a. So if this distance is r plus a, which is z. So you can integrate from r minus a to r plus a. That is one case, right?
Hmm.
Correct. To cover the whole thing. So you will get minus gm by 2ar, r plus a minus r minus a becomes 2a. So it cancels 2a down and becomes minus gm by small r, right?
Yes, sir.
So this is the case when the point is outside the sphere or spherical shell. If there was case 2 where the point is inside the spherical shell, so imagine that the point is somewhere here, right?
Hmm.
Everything is the same except limits are different. So minus gm by 2ar integral dz. Now you think about the limits. If the point P is here and my shell is here, this distance is actually a minus r, right? Because r is
Yes,
called
sir.
this distance.
Yes, sir. Yes, sir.
So a minus r, and if the other shell is here, the distance from this to this point, it will be a plus r.
A plus R.
And this time it will become a plus r minus a minus r, so 2r. So minus gm by 2ar into 2r, it will become minus gm by small a, right?
Hmm. Yes, sir.
Potential is coming like this, and the other case is when it is on the sphere. In that case, both the cases, the answer will be gm by a, because one time the distance will be 0, one time the distance will be 2r,
Hmm. Yes, sir.
right?
Yes, sir.
So what is important here is first of all to realize what this means. This means first of all that if the point is outside the spherical shell, potential is as if this whole spherical shell was a point mass.
Yes, sir.
First of all, like if this is the situation, point is here and this is a and this distance is r, the potential has come out to be minus gm by r. But this is mass m. On the other hand, if the question was simply mass m at one point, point mass m and distance of r, then also you would have said minus gm by r, right?
Yes, sir.
So if a point is outside a spherical shell, then the spherical shell actually doesn't matter. It behaves almost like a point mass, right?
Hmm. Yes, sir.
But if the point P is inside the shell, then the potential is coming out to be constant. Constant potential. It doesn't even depend on where it is. This R is not even in the formula. The formula depends on the radius of the sphere, right?
Yes, sir.
So it could be here, it could be here. It doesn't even have to be on the axis. Anywhere inside the shell, the V is this. It doesn't depend on the R, right? It is constant potential inside a spherical shell.
Yes, sir.
So
So,
that
so in this, can we directly conclude that the gravitational field would be gm by a square and gm by r square in both the cases, respectively.
How will you conclude that? On what basis?
So because gravitational potential is defined as gm by r square, and
Gravitational potential is defined as what?
sorry, I meant gravitational field is defined as gm by r square, and gravitational potential is defined as gm by r. So if they ask us for the field, can we just conclude that it's gm by r square directly in this case?
How are you concluding suddenly for field right now? On what basis are you concluding that? Do you know the field for a continuous uniform body is it defined as gm by r square for a uniform continuous body and not a point mass? What you are saying, the field formula is true only for point masses.
Okay, right. Yes, sir. Yes, sir. So,
If
so
you
if
can
we,
conclude that from there directly, then what is the point of doing all the integrations? Right now, all you can say is that the potential is this. It has been shown after integration. We could
no,
not directly
yes,
conclude
sir.
that
Yes, sir.
without doing integration.
Yes, sir. No, so I was asking, as in, if we are doing integration for the field, then we get the same thing like that way?
We will get something which we'll see when we do it, but
Okay.
uh,
So
first of all,
directly we
you
can't
don't
say that.
know. First of all, you don't even know the relation between V and E. Like right now, you don't know the relation between V and E. So you cannot conclude anything until first you realize what is the relation between V and E, and you cannot conclude anything directly on the basis of hope. Nobody would have known that potential inside the sphere is constant without actually doing the integration.
Yes, sir.
And you could not have guessed that potential for a point outside will be like a point mass without doing the integration. It has come after some work, not randomly out of thin air. You cannot directly conclude anything in science without some evidence.
Yes, sir.
All we know right now is that this is the potential due to hollow spherical shell. We don't know anything else.
Yes, sir.
For a point outside, it is as if the shell is at a center point mass at the center. For a point inside, it is as if it is a constant potential here. That's all that you know, and nothing can be concluded directly from here.
Yes, sir.
When we derive the relation between potential and field, after that we can conclude something, but definitely not right now.
Okay. Yes, sir. Yes, sir.
Once you know the hollow spherical shell derivation, after that it is due to a solid sphere. Potential due to a solid sphere. You will be using the shell derivation here. So again, there are multiple cases. Now it is a solid sphere of mass m, radius same a, point is somewhere here, distance between center and the point is r. Now what we need to derive is potential due to this situation. What we will use now is the derivation in the previous section, because now we know what happens if there is a spherical shell. So we can take two spherical shells. If we take two spherical shells, then in their middle, you can isolate a small volume, which is a solid volume, right?
Yes, sir.
Which will have some mass. So basically, the idea is take a spherical shell of radius x, take a spherical shell of radius x plus dx. Between them, there is a solid volume which will have mass dm. And that is like a hollow shell. There is a shell here. Is everyone understanding how there is a shell?
Yes.
Yes.
You have cut out everything else. There are two layers, one layer of radius x plus dx, one of x, and in between there is mass. That behaves like a hollow shell, and we know shell formula. We know potential due to shell at point P. That will be, because the point P is outside right now, you can say it will be minus GdM by, as if the shell is at the center, right? If you forget about everything else, just think of the shell. The point is outside the shell. So the formula will have R in the denominator.
So that is only if you're considering a shell which is around the center, right?
So what other shell are you considering? Is there any other type of shell that you will consider?
I thought you were considering a random shell at a certain distance from the
Shell at a certain distance.
No, I was saying that I thought you were considering a shell which is at some other distance from point P, like a general case.
Like a general case here, one shell here in the space imaginary.
No, sir, not like that. As in,
Like
not around the center. It's just a never mind. I got it.
what kind of shell? Like this shell you will consider here? Huh? This shell. Is that useful? Can you integrate this shell to cover the sphere?
No, sir, not like that. As in, if we have a sphere, right, and if we are considering a shell which is such that it is around the center, then that can be one case. But then let's say we move that shell a little bit up. So
A little
that's
bit up like this. Right?
exactly. Yes, so like in a 3D diagram, it'll be like let's say it's at a distance of some d from the center. So then we'll be able to get it.
Why would you move that up? Because that helps you integrate. Yeah, finally, you will integrate this shell to cover the whole sphere. Like, how do you plan to finally calculate the whole sphere's potential if you have taken a shell like this, which is off center?
It won't look like that, right? It'll be like
Whatever you want to
a
make
strip,
it.
a strip around the.
What?
It'll be like a strip around the sphere, right? If we just look at it from one side instead of a circle over there.
It will be a strip around the sphere. The mass is only on the, like this you're saying.
Exactly. Yes, sir.
Oh, exactly. So mass here on the inside of the sphere will not matter, only the surface will matter.
Yes, sir, that's what you said.
That's what I said.
So at least that's what I understood. I thought you just said that we're considering a shell, right? So I thought this is what I visualized.
Arin, what have you understood?
Sir, sir, what she said is for finding the potential of the hollow sphere.
Yeah. Right now we have a solid sphere. How will you plan to take account of masses inside if you take a shell like this? How will you take into consideration these masses if you take a shell like this?
So we'll have to integrate twice.
Integrate thrice.
Twice.
Twice. How? Twice? This shell has mass only on the surface, and if you vary it, all you get is the outer hollow spherical shell.
Yes, sir, exactly. And then we'll
Uh-huh.
integrate different hollow spheres. So
Oh,
integration twice.
how different hollow spheres? How will you integrate that?
Oh, so basically what I'm saying is basically using the spherical shell formula that we derived before. So never mind, I got it. I was just so never mind.
What am I doing right now? I'm doing the spherical shell formula.
No, sir, you've already done it. So I thought you again considered the same ring as the previous case, but then I realized that you're considering a full hollow sphere inside it.
Obviously, why would I derive the hollow spherical shell formula again?
Yes, sir. That's why I was confused.
This is a sphere, this is another sphere, this is another sphere, this is hollow spheres.
Yes, sir.
I'm going to take two spheres, x plus dx. In between, there will be some mass. That will be my hollow spherical shell. Due to that, the potential is this if the point is outside. Is this formula clear? Whatever is the mass of that shell, this point is outside, so formula is this.
Yes, sir.
Now we have to find the mass in this. The mass in this has to be found out. That is easy because now you have mass in the whole sphere. So mass density will be mass by volume. And you have to multiply the density with the volume inside these two. So volume inside these two will be 4 pi x squared dx. Can anyone tell me why it is this?
So this is the volume for what again?
What do you think?
So like, can you repeat your last statement once, please?
This is the volume inside this where the mass is between the two hollow spheres. What volume are you supposed to consider? Wherever is the mass dm, that volume.
So it'll be so one sphere is 4 pi x squared, and that has a depth of dx. So you multiply 4 pi x squared depth of dx as if you're considering all those spheres together with a tiny depth of dx. Then you multiply 4 pi x squared with
4 pi
dx
x
to get the
square is the
volume.
surface area of the inner sphere multiplied by dx should be the volume in the space.
Yes, sir.
4 pi cancels. Your dm mass is coming out to be 3m x square dx by a cube. Now your dv will be minus g3m x square dx by r a cube. This is your dv. Now we just have to integrate it. If the point is outside, this is the situation. You have to cover minus 3gm by r a cube. All of these are constants, and x square dx. You have to integrate x square dx. So the x is the variable. So integration will be from 0 to a, so that you can cover the whole sphere. Right?
Yes, sir.
Yes, sir.
So when you integrate this, it will become x cube by 3, so a cube by 3. So all of it gets cancelled, and a cube by 3 gets cancelled. You get minus gm by r. So again, that is a very nice result, which says that if it's a solid sphere and the point is outside, then also potential is almost as if it's a point mass at the center, right?
Yes, sir.
It is not obvious before you do the integration. It has come after some effort.
Yes, sir.
Do not always assume that it will be true. It will not be true if the mass is non-uniformly distributed here. If there is different density of mass, all of this is gone.
Yes, sir.
It is coming only for a solid sphere with uniform mass density. Potential outside is looking like it's a point mass at the center. The other case is when the point is inside. Point is inside, let's say here. This distance is r, radius is a, and now you have to consider this situation. So first of all, we will draw a line like this, which will mark out a hollow sphere till the P point, right? If you take any shell outside, right?
Yes, sir.
Basically, you consider two cases. Case one is for outside shells, right?
Yes, sir.
And case two is for inside shells, inside the P and outside the P. So the difference happens because for outside shells, the formula of potential will be different, right? Minus G dm by A, right?
Yes, sir.
And for inside shells, the formula is minus G dm by R, right?
Yes, sir.
So everything is the same. The minus 3 gm by a cube integral x square dx, what we got earlier, is the same, but no, it's not the same actually, because the formula is only different. So we'll have to do it properly. So minus, for inside shells, let's write the formula. Dm was coming out as what? 3m by a cube x square dx. 3m by a cube x square dx, and by r. R is the distance. If there's an inside shell like this, which has radius x, r is this distance, right?
Yes, sir.
So for this, the formula is the same. R doesn't matter, r is fixed here, and you just integrate it, but you integrate from 0 to r, right?
Yes, sir.
You understand what I'm saying? Because it is an inside shell, you have to integrate all shells inside up to the r radius, right?
Yes, sir.
Minus 3 gm by a cube, and this will become x cube by 3, so r cube by 3. So it will be minus gm r cube by a cube, right?
Yes, sir.
Yes.
Here, when it is outside shells, this part will become minus g 3m by a cube x square dx by a. A is, by a means actually the radius of the shell. So radius of the shell would be x, right?
Yes, sir.
Is everyone understanding how I'm writing this?
Yes.
Radius of the shell is x. Integration now goes from x varies from r to a. If you think about it, r to a, right? Because you have to take all the outside shells now. So they start from r, x starts from r and goes up to a, right?
Yes, sir.
Minus 3 gm by a cube x dx integration. So it becomes x square by 2, and you integrate it like that. So a square minus r square by 2, right?
Yes, sir.
Okay. I hope I've not made some mistakes on you. I feel like I made a mistake somewhere. Inner part is correct. Inner part potential. Actually, V1 plus V2.
So it should have been R square, but we're getting R cube.
1 second. R cube by A cube is the mass and divided by R. Yeah, we are making some mistake here. GM by R. DM was what? DM was DM was the mass of that portion. So 3m by A cube x square dx and by x, right? By x or by r actually. What we can do is much simpler. We don't need to integrate it also actually. What we can do is simple. If you are taking an inner part here and this is the point P, this is the distance r, total radius is a. So all of the inner part can be thought of from the previous case where we have derived solid sphere at a point P, right?
Yes, sir.
The only difference is that the mass here is m dash instead of m.
Yes,
Whatever
sir.
is the mass inside is lesser now. So in the previous part when we had found V was minus gm by r, that was for a point outside a solid sphere. Now it is minus g m dash by this r, right?
Yes, sir.
Where m dash is the mass, whatever is inside. That is easy. M dash would be equal to m into r cube by a cube, right?
Yes, sir.
Is everyone understanding why this mass is this?
Yes.
Because you can do density and stuff, but it will be proportional to r cube, right? Because volume is proportional to r cube.
Yes.
So you will get minus g m r cube by a cube by r, and you can get r square by a cube. So in the previous integration, I made some mistake. You can check it yourself, but it is obvious that it has to be minus g m r square by a cube. And this is due to the outside part. Add these two, you get total potential at T, right?
Yes, sir.
Total potential at T is shown in 11.12, the exact formula. And that is for an internal point. So you have to remember that formula. So remember it like this, minus gm by 2a cube 3r square minus 3a square minus r square. And one good way to remember is you remember the limiting values. When P is at the center, you should remember potential should come out to be minus 3 gm by 2a. Remember the limiting values, because then you can say that if you make any if you have any confusion in the formula, you can put r is 0. Does it come out to be this? Right?
Yes, sir.
Remember this value, and then you can not make mistake in the exam here with the sign and all. Because the formula should give you this. And remember that if r is equal to a, the formula should give you minus gm by r is equal to a, it will become 2a square gm by a. Right?
Yes, sir.
So at the center, at the surface, these two values you should remember so that you don't make mistakes in this potential. So potential inside a solid sphere is complicated. if it is a hollow sphere, this is hollow. Outside point is minus gm by r. Inside point is minus gm by a. If it is solid, outside point is minus gm by r. Inside point is this formula, right?
Yes, sir.
All of these derivations will become super important when we start doing fields. We'll have to do the same calculation for field also. But later when we see, we will avoid doing integrations there because we'll use these formulas, right?
Yes, sir.
Like whenever the field calculation is becoming complicated, we don't want to do integrations of these types of spherical situations. We want to use the potential formulas developed and derive field from there. So next class will be about understanding the connection between V and E and using these to find E in different situations. Also, all of these derivations are valid for electric field situations. So electric potential energy, all of it is defined in the same exact way. And you should read those sections now. And all of the calculations are valid, except that in potential, you put K Q by R. Instead of minus G, you'll put K. Instead of M, you'll put Q. Every formula will change slightly, but it will be almost exactly identical. Okay.
Yes, sir.
So read the field chapter, also chapter 29, while you are reading this and see the connections between the two. Next class will be about the connection between V and E and calculations of field. Read the remaining parts of the chapter gravitation
Yes, sir. Yes, sir. So when is the next class?
tomorrow.
Physics only, sir.
No, maths. Okay,
Oh, okay. Yes, sir.
that's all for now.
Thank you, sir.